There is a point on the Yangtze River in central China where a wall of concrete rises higher than a 60-story building and stretches nearly 2 kilometers from bank to bank. Behind that wall, the river does not simply slow down, it disappears. In its place, a reservoir nearly 600 kilometers long swallowed valleys, towns, and mountains that had stood above the waterline for thousands of years. The structure behind all of this is the Three Gorges Dam, and the number that defines it is not the height of the wall or the length of the reservoir. It is the power output, 22,500 megawatts of installed generating capacity, more than any other power station on Earth. That figure alone would seem to justify nearly anything, and for decades, that was more or less the argument made by the engineers, planners, and government officials who championed the project. China needed electricity on a scale that conventional sources could not match. The Yangtze River, the longest river in Asia and one of the most flood-prone waterways in the world, had killed hundreds of thousands of people across the 20th century during its worst flood seasons. A single massive dam, proponents argued, could do two things at once: generate clean power for hundreds of millions of people and regulate floodwaters that had repeatedly devastated the densely populated middle and lower Yangtze basin. On paper, both goals were achievable. The engineering was not the primary obstacle. The obstacle was everything the reservoir would consume in order to exist. The Three Gorges region is not remote wilderness. It is one of the most historically continuous inhabited landscapes in China. The gorges themselves, Kutang, Wu, and Jiling, had been carved by the river over millions of years, and human civilization had built along their edges for most of recorded history. When planners drew the reservoir boundaries, they were not drawing lines across empty terrain. They were drawing lines through cities, counties, and villages that had existed for centuries. The rising water would not spare cultural sites, farmland, or the communities whose livelihoods depended on the river's natural rhythm. Construction on the dam began formally in 1994, though the project had been discussed and debated in China for decades before that. The scale of what was required was staggering, even before a single turbine turned. The concrete gravity dam design, meaning the dam holds back water primarily through its own enormous mass rather than through an arch or embankment, demanded an almost incomprehensible volume of material. Workers and equipment operated continuously across multiple years, and the logistical coordination required to sustain that pace of construction across a remote river canyon represented an engineering challenge in its own right, separate from the structural problem of building the dam itself. The turning point in the dam's story is not the moment the concrete topped out or the moment the generators came online. The turning point is the moment the sluice gates began to close and the reservoir began to fill. That is when the scale of the displacement became undeniable. More than 1 million people had to be relocated before the water reached its operational level. Entire cities did not just flood, they were deliberately prepared for flooding, with residents moved to newly built towns on higher ground, and then they were submerged. Archaeological teams raced against the rising waterline, attempting to document and, in some cases, physically move artifacts and structures before they were lost permanently. Much was saved, much was not. The mechanism that makes the dam function is straightforward in principle and extraordinary in execution. Water from the reservoir passes through intake structures on the upstream face of the dam, drops through penstocks, and drives the blades of massive turbines housed in the powerhouses at the base. The Three Gorges Dam has 32 main generating units, plus 2 smaller units for the facility's own power needs. When the reservoir is at full capacity and seasonal precipitation is high, the generating output can be exceptional. After the monsoon season of 2020, the dam produced nearly 112 terawatt-hours of electricity in a single year, surpassing the previous world record of 103 terawatt-hours set by the Itaipu Dam in 2016. On average, accounting for seasonal variation in river flow, the dam generates around 95 terawatt-hours per year. That range, between roughly 75 and 115 terawatt-hours depending on rainfall, illustrates a critical truth about hydroelectric power. Its output is ultimately subject to the weather in the river's drainage basin, not just the engineering specifications of the dam. The cost of building and operating the dam is inseparable from the cost borne by the people and the landscape it displaced. Relocation of more than 1 million residents was not simply a logistical exercise, it was a profound social disruption. Farming communities lost land they had cultivated for generations. Urban residents lost the fabric of neighborhoods and local economies. Some relocated communities reportedly struggled to adapt to new environments that lacked the agricultural conditions or economic infrastructure of their original homes. These human costs exist alongside documented environmental changes, altered sediment transport downstream, shifts in the river's ecology, and the ongoing question of how a reservoir of this scale interacts with the geology beneath it. There are voices, both within China and internationally, who argue that the dam's benefits justify its costs. Flood control along the middle and lower Yangtze is a measurable outcome. The dam's reservoir can absorb excess water during the heaviest rainfall seasons, reducing peak flow downstream and protecting cities that were historically vulnerable. The clean electricity generation replaces coal that would otherwise have been burned, representing a genuine reduction in emissions relative to the alternatives available at the time of construction. These are not trivial arguments. But critics point out that the full accounting of environmental and social consequences was contested before construction began, and some of those contested consequences have since materialized. The uncertainty that surrounded the project's approval did not disappear when the concrete cured. Today, the Three Gorges Dam operates as the world's largest power station by installed capacity, a fact that remains unchallenged. The reservoir it created is a permanent feature of the landscape of central China, and the communities displaced by its construction have been resettled with varying degrees of success into a new geography. The Yangtze still flows. Downstream, it flows differently than it did before, carrying less sediment, responding differently to seasonal variation, supporting a river ecosystem that has had to adjust to a fundamentally altered set of conditions. What the Three Gorges Dam ultimately demonstrates is not that megaprojects are right or wrong by nature. It demonstrates that when an engineering decision is made at sufficient scale, the consequences are proportional to that scale in ways that extend far beyond the original engineering problem. The dam solved a genuine problem, chronic flooding and chronic electricity scarcity, with a genuine solution. The solution required the creation of an inland sea where a river valley used to be, and an inland sea, once made, does not unmake itself. The next question the Yangtze forces engineers and policymakers to answer is not whether the dam should have been built, but how a river system permanently altered by one of the largest structures humans have ever constructed can be managed across the generations that will inherit it. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.